Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, EDISON International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
I'm Marylou.
And in studio, we have a third M, Mackenzie, with us today. Mackenzie, if somebody needed to get a hold of us, what would they need to do?
For math homework help, call in Bakersfield 636-437 or 4357. Sorry.
There you go.
Toll free 1-866-336-6284. Email dothemath@kern.org. We're online at dothemathonline.net and on social media, Facebook, Instagram, Twitter, and YouTube.
There's a lot of sixes in there, aren't there?
Yes.
Yeah, a lot of numbers to go right there. Anyway, a lot of different ways to get a hold of us here at Do the Math. Now, before we get started on today, why don't you let everybody know where you go to school and what grade you're in?
I'm in 6th grade at Leo B. Hart Elementary.
And you've been at Hart for a long time, or is this your first year, or are you pretty new?
Long time.
Long time. Since the good old days, like when you were 2 years old?
Since kindergarten.
Since kindergarten, all right. So you've been there a long time. So this year obviously is a little different.
Mm-hmm.
Is there anything good about this year?
I've gotten better at doing things on computer, like typing and navigating.
There you go. See, so there are some positives out of this, right?
Mm-hmm.
So you're getting a lot more, let's say, literate, right, at using the computer, right? Your typing skills are getting a little bit better. You're able to better communicate with the computer and through video meetings and conferences and stuff like that you probably didn't have to do before.
Yeah.
Right? I didn't have to either as far as teaching kids, right? But we're all kind of getting the hang of it now, right? And I think we're all a little bit better at doing that kind of stuff right now.
Yeah.
All right? If you could go back to school right now, and they said, you can come to school, but you must wear a mask all day long, would you go back to school right now?
I would, because I still want to see everybody. It stinks I have to wear a mask, but at least I'm going to see everybody again.
Okay, so you'd like to go and see everybody. You know, if I have to wear a mask, I'll wear a mask all day, right? But there you go. So you'd like to go back and see everybody. Well, we do have phone tutors available until 5:30, most Tuesdays and Wednesdays throughout the regular school year. The phone numbers are at the bottom of your screen periodically throughout the program. Time now for today's Math in the News. All right, and today's Math in the News, literally ripped right out of the paper on Monday. So it says, when we fall for the 99-cent trick. Have you ever fallen for the 99-cent trick?
I don't know what it is.
Yeah, you don't even, you're like, what are you talking about, old man? I don't know what you're talking about, 99-cent trick. All right? It's called our left digit bias. All right? So we'll go ahead and take a look at the camera right here and kind of explain what's going on a little bit. So the mind compares the leftmost digits before it rounds up the numbers. That is called the left digit bias. Okay? Now, when an item is priced at $2.99, the idea is the consumer will think of it as $2. People look left first, okay? So, left digit bias, does this make sense to you? When they say it's $2.99, they did studies and they go, people look at that left digit first and they just see the 2, so they think of it as $2. Does that make sense?
Yeah.
Yeah, all right, so you understand what's going on, right? This big study they did. So that is left digit bias. Just like we read from left to right, the same thing with numbers. Okay? So that's if you see something individually. All right? So just below pricing. All right? This is the next thing they had in the article. Peanut butter. If you see it by itself at $2.99, people will go, all right, it's $3. All right? They go, all right, it's $2.99. Yeah, I know what you're doing with the 99, but it's $3. But when $4 is side by side with the $2.99, the brain compares the 4 to the 2.
Interesting.
It is, right? Because if you go, all right, well, I see it by itself, $2.99 is going to be 3. But if I see $2.99 next to 4, I think it's 2. That's the left digit bias and the just below pricing right there. And they have spent, as all studies, an incredible amount of money and time on this to see how this happens and why it happens, okay? So I figured, all right, there's our math, right? So I wanted to do something else with the 99, okay? So this is just a fun little fact. 99 can be written as 2 cubed plus 3 cubed plus 4 cubed. And you do all of those. Now you know about exponents, right? Mm-hmm. What does 2 to the third power, 2 cubed, mean?
2 times 2 times 2.
Right, which is why we get 8. Because sometimes people that don't understand exponents fully, they look at that and they go, 2 to the third power, that must be 6, 2 times 3. But you explained it beautifully. What about the next one?
Next would be 3 times 3 times 3.
Right, so you got to do it 3 times. So instead of that being 9, you need to do it 1 more to get to 27. Mm-hmm. And what about the 4s?
It would be 4 times 4 times 4.
What's 4 times 4?
16.
And what's 16 times 4?
64.
Yeah, there you go. It's right there, right? I was trying to see if I can throw you off real quick. But anyway, that is today's Math in the News, the 99-cent trick. I don't know if it's a trick. I mean, we just kind of explained what was going on right there, but it's the way consumers look at things. And they go, all right, well, you know, if it's $2.99, I know it's $3, but oh, it's right next to that one. Well, that's really only 2 because that's 4. Just one of those things, all right? Anyway, we do have phone tutors available until 5:30 this afternoon. Right now, we've got Bo online. Bo, how are you today?
Good.
Good. Now, you're a 6th grade student calling from Rio Bravo Greeley, correct?
Yes.
All right. As soon as you're ready, let's hear the first problem that you're working on.
Okay. My first problem is 3 over 2 divided by 1 and 5/7.
3 over 2 divided by 1 and 5/7. Bo, did I write that correctly?
Yes.
Okay, so Bo, what do you know about the 3 over 2? Is that good to go? Can we leave that the way it is?
Yes.
Yes? Okay. And what about the division sign? Should we leave the division sign the way it is, or do we need to change that?
I think we need to times it.
Okay, there you go. I think you're right. Now let's talk about the 1 and 5/7. Is that good the way it is, or should we change that up?
No, we need to break down the 1.
Break down the 1. Very good. We don't want a mixed number now, do we?
No.
No, we want to change that. So how am I going to break that down? Where am I going to start at? The 1, the 5, the 7? Where am I starting?
1 times 7.
Is it 1 times 7 or is it 1 times 5? Oh, wait, you're right.
I think it's 1 times 7.
You are right. It's
Hey,
1
don't let her
times
throw
7.
you off, Bo. You know what you were doing there.
It's 1 times 7, which is what?
And 7.
Okay, and then what are we going to do with the 5?
Add it.
Add it. Very good. So we times and then we add, right? So what is that going to equal?
7, 8, 9, 10, 11, 12.
12 over 7. Are we good to go? Can I just put that straight down into our new equation?
Yeah.
I can? We changed that division sign to multiplication. Because I changed that, Bo, have you heard
we
of...
need to flip it around.
We have to do the reciprocal, don't we?
Yep.
So yeah, we want to do 7 over 12. We don't want to do 12 over 7. We want the reciprocal because we changed that division to multiplication. Now, is there anything you can do before we solve this problem, 3 over 2 times 7 over 12? Have you been taught to simplify within the problem?
No.
Okay, well, can I show you? So
Yes.
we want to look at our diagonal numbers, okay? I'm not looking at the 3 and the 7. I'm looking at the 3 and the 12. Is there a common factor that goes into both 3 and 12?
Common factor.
A common, 3, very good. So I can actually divide both of these numbers by 3, can't I, Bo?
Yeah.
So if I divide them by 3, what's 3 divided by 3?
9.
With 3 divided by 3.
Oh,
not,
3 divided by 3.
Yeah.
3.
well, it's actually 1, right?
1, yeah, 1.
So we have 1 over 2. And what is 12 divided by 3?
12 divided by 3 is 4.
4. Look at Bo, we simplified within the problem. Now you tell me, how are we going to solve this out? What do we do to the numerators?
We need to divide them.
Not divide, we're multiplying, right? We have a multiplication sign here, so we're going to multiply straight across. 1 times 7 is?
1 times 7 is 7.
Very good. And what's 2 times 4?
2 times 4 is 8.
And there you go. And you know what, Bo? You don't even have to worry about simplifying because you already did it within the problem, okay? So we know that 3 over 2 divided by 1 and 5/7 is equivalent to 7 over 8.
Does that help you out, Bo? Does that make sense?
Yeah, that makes sense. Thank you.
You're
Okay,
welcome.
now, Bo, are you still online?
Yes.
I think you had one other problem too, didn't you?
Yes.
Okay, let's hear the other problem that you had as well.
And it's 3 and 3/10 times 1 half.
Times, is that correct, Bo?
Yes.
Okay, so you lead me through this one, Bo. What's the first thing we need to do?
We need to break the 3 down.
Okay, break this down for me. Break this mixed number down.
And 3 times 10 plus 3, so that's 33.
Over.
Oh yeah, 33 over 10?
Very good. And do we keep the multiplication sign?
No.
Oh, yes?
Yes.
Okay, so we're going to just bring 1/2 straight down. And there's no, 2 doesn't go into 33, does it?
No.
No. And we already know this is already simplified. 1 goes into 10. We can't simplify that anymore. So, Bo, what's our next step? What do you think we're going to do with the new?
Times it?
Yes. Okay, times those numerators for me.
Okay. And 33, right?
Right. And what's my denominator?
And 20.
Okay, but are you happy with that answer, or can we fix that a little bit?
We need to fix it.
How do I fix it?
We simplify it.
Very good. Very good. So how would you simplify this, Bo? Let's
Oh, you minus it.
Okay, we minus it, but before we minus it, ask yourself, how many times does the denominator go into the numerator? So how many 20s go into 33?
1.
1, very good. Now you minus it. What's 33 minus 20?
13.
Very good. And what is my denominator?
20.
And are you happy with that answer, Bo?
Yes.
I think you should be. Very well done,
I
Bo.
was
Good
going to say,
job.
I'm happy with it too. Nicely done, Bo. You got both of those problems correct. Wanted you to do the other one just to make sure that you were a little bit more solid on how to do those problems. And for your great effort today, you've got yourself a meal courtesy of our friends at Chick-fil-A. So congratulations on that. All right, well, you can do just like Bo. Give us a call. We are here until 5:30. Time now to go see how they're doing math outside of the classroom.
We're here at Taft College today. We're in the lab. We're on campus. We've got an amazing crew of students helping us out today. And today we're going to talk with Professor of Life Science here, Greg Galling. Greg, thank you very much for having us in your lab today. We have a really exciting experiment that may share some relevance as far as the way that our viewers may interact with the world today.
Yeah, basically what we're going to do is we do sort of a hand washing experiment, but we're going to look at the bacteria that are kind of currently on your fingers, things you picked up through the day, go through a pretty rigorous hand wash, and then it's sort of looking at how well did we clean our hands off, but there's also some other lessons we'll learn from this, the kind of interesting results we get in the end.
Now, a lot of kids are going to look and they're going to brush off this idea, I don't got to wash my hands, I don't see anything on there, right? In full transparency, about 45 minutes ago when I left my house to come here today, I put some hand sanitizer on. So the only things that I've been able to interact with my hands have been the steering wheel inside my car, maybe opening up some handles. But the idea is just because you see it doesn't necessarily mean it's there. And what this does is bring that into vision.
Yeah, bacteria, you can't really see them with the naked eye, but they're all over us. In the average person, depending on their size, you're looking at maybe 10 trillion, 100 trillion bacterial cells in and on us. So it's just, it's a great mystery. Just because you can't see it doesn't mean it isn't there.
So we've got some dishes over here that we're going to utilize and kind of walk us through this experiment and what we're going to do.
So what we have, it's just it's a petri dish and it's got a nutrient auger. So there's lots of things that bacteria like to eat, and they'll grow on top of the surface. Kind of like if you've had you leave bread out or fruit out for a couple of weeks and you start to see the little, green mossy stuff growing on it, except we're looking at bacteria instead of fungi. So what we'll do is we're going to take a look at what's on your hands now, sort of a pre-washing. We'll wash our hands and then we'll take a look with 3 fingers and see what's on after we wash our hands.
So there's going to be kind of a before and after of filth on my fingertips.
Pretty much,
Okay.
yeah.
Well, let's go ahead and
Okay.
I believe our producer Aaron's going to be joining us on this experiment as well.
Yeah, so if you want to go ahead and set up your plates, just kind of draw a line. I've got a Sharpie, I can get another one. And just draw a line down, one side write pre, the other side post, and maybe your initials. And then just with your 3 fingers on your right hand, just kind of gently touch them to the Petri dish. And it feels just like Jell-O, okay? And then we'll put the lid back on, wash our hands, and once they're dry, then we'll go ahead and touch the post side.
Okay. So Aaron, go ahead and take care of yours. I'll go ahead and start the press here. All right. You can't see the lines through there. This was the pre side, so I'll go ahead. Does it have to be a certain 3 fingers? Can it be
You just-
pinky to middle? Can it be pointer to
I'd
ring?
get the index in there because that's one you tend to use a lot.
Sure is. All right. 3, 2, 1. Just a little press. Didn't have to be too hard there.
We
Enough
got
to
the
see the
fingerprints.
fingerprints. Okay. So we've got the 3 fingers in there, and now the next part of this is 2 minutes of hand washing,
Right.
plus about 45 seconds of drip.
Yeah, just let it air dry. If we use a paper towels aren't sterile, so you could be spreading something else on it. And I'm just going to cover these up. Again, the whole unseen world out there. Right now, there are bacteria falling. We don't know it. And, some could have landed on here. But we'll know in the end if any did or not. But so we've got a couple of sinks here, some soap dispensers. I have them get, kind of fill up about 4 or 5 pumps of the soap. And I'll turn the water on for you. Better if it's a little bit warm, but go ahead and just really rub the heck out of those. Try to get any traces of fingerprints off. I don't know if you want to use that sink or.
Well, somebody's counting to 120 here, so I know
We
when to
start?
stop.
Yeah. All right, so we'll
So-
say that's been about 15 seconds.
As enthralling television as it is watching me wash my hands, we're going to go ahead and come back. And for our next break, we're going to go ahead and throw these into the incubator. We're going to talk a little bit about what that does. And then we're going to get a look and see exactly down the line what this looks like as we skip forward through time. But until then, we're going to throw it back to the studio, Mike. Take it away.
All right, thanks for that, Devin. Also, thank you to Taft College and Dr. Galling out there. Right on cue with what everything is going on, right? I mean, it's an actual class that they teach out at Taft College, but has a lot of relevance right now as far as what everybody is doing. So, we do have phone tutors available until 5:30 most Tuesdays and Wednesdays throughout the regular school year. The phone numbers are at the bottom of your screen right now. We have Mackenzie, a 6th grade student from Hart, and you've been a Hawk for many, many years now.
Yes.
All right, you ready to do some work?
Yes.
I know you kind of like been hanging out like, hey, when am I getting to do some math? Well, here you go. Here's one right out of your book, and you're working on this in class right now with measurement and conversions. So the problem they want you to work on is convert 226 ounces.
Okay, go ahead and write 226 ounces.
And they want you to turn that into pounds. So 226 ounces is equal to how many pounds? And what they're doing is they're showing you a conversion factor. All right? And it says 1 pound is equal to 16 ounces.
So let me write this for you. I'm going to have you write it for me.
Okay.
There we go. So it was 1 pound equals 16 ounces, right? There's our conversion. So we need to go from ounces to pounds, right? So how would you set this up? What are you thinking? Put it, how about equals?
Okay.
Let's,
If that looks weird now. Oops.
okay, so we need to get from our, and put our pounds, right? So we know it's 1 pound equals the ounces,
Yeah.
right? So what we can do is we can go ahead and cross out the ounces, right?
Yeah.
Because our answer needs to be in pounds, okay? So yes, you're right with multiplication. So we can multiply across because we made fractions, right?
Yeah.
So if we multiply across, we have 226, right? So let's go ahead and multiply across. Now what do you think we need to do to solve that?
Divide it.
Got it.
So
Or you could go over here. There's lots of space over here. And talk me through what you're going to do, okay?
16 goes into 22 one time. Subtract it. And then borrow. That looks weird, but I know what it says. And I'm going to bring down the 6. 16.
And do you think how many times does 16 go into 66?
I'm going to guess 4.
Okay, let's
I'll
try it.
try it.
I love the way you're guessing and checking. And pretty close? Yes? Okay. So I'm going to move this up for you. And I don't know, does your teacher prefer a decimal, a fraction?
Class, we've been doing a fraction.
We've been doing a fraction. Can you make a fraction out of your answer?
216.
Well,
Well.
how many whole do we have? We have 14, and what's left over? But are we done with that?
We can simplify that.
Very good. And tell me how to simplify that.
They're both divisible by 2, so we can divide them both by 2. Now that's getting kind of, let's do it down here. Equals 1/8.
So let's go ahead and write our answer over there. What's our final answer?
Equals 14 and 1/8
There you go. So we know that 226 ounces is equivalent to 14 1/8 pounds. Nice job.
There you go. Nicely done. So go ahead and erase the board.
There's a little red X at the bottom there.
This?
Right down. Where did I go? Right there. There you go.
It's my fingerprint.
Now, Mackenzie, I know that you are an excellent student and you are ready to do any type of problem, which is why we're going to take a look at one of your homework problems and we're going to discuss this one. This is a classic problem. I know that somebody just phoned in and wanted to see this problem also, so it's perfect timing. Hopefully all of the kids that have this problem for homework are viewing at this time and will be able to see it. So, this is dealing with measurement and conversion, just like you are doing in your class right now. Mick drove 1 mile to his place of work at 30 miles per hour. So you guys can draw, write whatever you need to up there. You're going 1 mile and you're going 30 miles an hour. If Mick wanted to average 60 miles per hour on the round trip, okay, that means he's going home to work and then back home again. So he's going to be traveling 2 miles.
Okay.
All right? They want to know how fast would he have to travel on his way home, and the answer is not 90. Because a lot of students would see and go, well, if I go 30 and the average is going to be 60, I need to get 120 divided by 2 to get 60. But that's not going to work. So I would like you to explain with Mackenzie how this works and what the answer is.
Mackenzie, let's start with the 1 mile at 30 miles per hour.
Okay.
So if we are going from home, okay, and we are traveling to work, okay, I'm going to do a straight line here. How long would that take us driving the 30 miles, you know, the 1 mile, 30 miles per hour? How long, how much time does it take? How much time would that take? Is it 2 minutes?
Yeah.
Okay, so we know it's like 2 minutes, okay? We know that that's going to take us 2 minutes. So when I hear this, the first thing I think is, oh, 30 miles to work, 30 miles back home, 60. There you go, right? A total of 60. But it's not a total of 60, is it? It's average of 60. So what are your thoughts on this?
Well, I tried to do what he said, and then I don't.
So kind of explain how you did this.
I did it. I don't remember how I did it.
What did your average, what were you using to get your average of 60?
I knew an average is you add up all the numbers and divide by how many you had.
Perfect.
And then I found out that 30 plus 90 equals 120 divided by 2 is 60. But the answer is not 90, so.
There you go. Because we need two numbers, right? We go to work and we come back. And those two numbers together have to average 60. If I, again, added 30 plus 30, that totals 60, but the average would be 30, right? So that is going, if we need to average 60, right? And the 60 miles an hour is going to take us 2 minutes. Can that be done? How long does it take us just to get from home to work?
2 minutes.
Takes us 2 minutes, right? But we need to average 60 miles an hour there and back in 2 minutes.
We already used up all the time.
Where do we use up all the time at? Where? Do we?
Just going there.
Yeah, just one way, right? So can you do that at all?
No.
No, it's impossible. We've already used up all of our time just going to work.
Okay.
See, so he gave you
So
an
the answer is impossible,
question.
right? Now, there are students that actually turned in their homework with this problem, and they said you would have to transport yourself somehow.
Yes.
You know, like in Star Trek and things
But
like
that still takes time.
Well, I would dare say if they had a second, they could go ahead and do it like that. But a couple of them, they get that you can't do that.
You cannot.
You've already used all the time.
Yeah.
So it's more of a logic and reasoning problem as well as the distance, rate, time thing. Because if you try to do the formula and set it up, it's going to be a headache. If you just logically think about it, that's the more efficient way, let's say, to go about it.
And that's where I started with this. I was trying to mathematically figure it out, but you can't.
Which is why a lot of students find it difficult. Now, when you get to junior high and high school, you're going to get that type of problem. And guess what? You're going to get it correct then, right? Because you're going to go, oh, I remember that old man gave me that problem right there, and I remember that's an impossible problem right there. So anyway, helping you expand your brain right there.
There you go.
636-4357 is the phone. Now, that's right. A little congratulations right there. We do have phone tutors available until 5:30, and we are going to go back out to Taft College and see how they're doing with Devin.
Hey, thanks a lot. Back here at Taft College. If you missed our first segment, we have some explaining to do. We washed our hands. We're here at Taft College with Professor of Life Sciences, Greg Golig. And we did a Petri dish experiment. We're exploring bacteria, the unseen invader. We did a pre-gel where we took our fingertips, pushed them in to see what would be there, and then we washed our hands to see what's left afterwards to kind of illustrate the importance of hand washing. So what we've been doing is we have been letting our hands kind of dry out. Aaron as well is joining us on this experiment. We're just about there where we're no longer dripping, and Greg, we're ready for the next step.
Okay, so what we'll do, you've got your Petri dishes. You've already taken your 3 fingers and just touched them to the pre side. Now you're just going to repeat with the same 3 fingers on the post side. Okay?
All right, so, and as soon as we do that, as we learned from our lesson, we want to put that cap back on.
Yep.
So we don't let any unseen bacteria from the air around us come back through there. Okay.
Yep. All right. And then what we would do now, so the plates are done, you would have deposited single cells of bacteria on the plate, and depending on the type of bacteria, they take about 20 minutes to divide. So every 20 minutes they go to 2, then to 4, and after about 18 to 24 hours, you could see this little mound of cells on the plate. And I have some of those if you want to take a look at different types of bacteria. So we'll put these in an incubator.
So tell us a little bit about the incubator, the conditions inside, and how that facilitates the growth of the bacteria inside the dishes.
Right, it's an excellent question. So the bacteria that hang around our bodies that cause disease, there's obviously things about us that they like, the food, the nutrients, and one other thing they like is the temperature. So, you know, like, just like with all of us, there are certain temperatures we kind of prefer to be at, and same thing with bacteria. So this is set basically to body temperature, around 36 degrees Celsius. And so we'll just put them in here, and these are some examples. Pull out this one. I've moved some of the bacteria around, but you can see this is about a day old. And this bacteria is called Bacillus subtilis. And it's something that you can find, actually, I don't know if you want to smell it, maybe you don't.
I'm good.
Yeah, if you did, it's going to smell kind of like rotten feet. And this is part of the reason why
I already got those.
you get foot odor. So anyway, that's what you'd look at after about 24 hours of growth. You put your stuff on, you don't see anything. 24 hours later, boom, there's these huge colonies.
So if we could estimate how many, I mean, we could use the amount that we see there to kind of estimate how many were there to begin with, kind of working backwards.
Well, we know each one of those little colonies, it starts off as exactly one cell. And as it divides, it's sort of like if you had a bucket of sand and you started pouring it out, and it starts to build up and spread out and build up and spread out. And what's kind of neat is each species of bacteria, they've got a particular way, like the little pigs, a way that they build their house. Some like to build kind of mounds, others are kind of flat. The colors are different between them. Some are really tiny colonies, others are kind of large and taking over the whole plate. And it's interesting because, again, each species has a particular way they all grow, they make their colony, they make their house in that same manner.
So it's not just about how, and it's not just about the fact that it's doubling, but how rapidly it's doubling that is going to let us know how aggressive some of these bacteria are in certain conditions.
Right. And those colonies that you looked at, you've got somewhere on the order of hundreds of millions to a billion cells in that colony. They're that small.
So I understand that our students here have taken part of this activity yesterday.
Yes, yeah. So You guys ready to see your results? You excited or nervous? I'm not really sure.
Hey, quick survey. Who's going to have the winner for the most full bacteria dish here? You don't have to point fingers.
Yeah,
We're
don't
rolling
point
here.
at me.
You know the
No.
answer.
All right, so I'm going to take those out.
So when we come back, we're going to reveal the winner of our events from our test from yesterday to see how rapidly just a small sampling of these just in one day can have as far as an impact on the growth of these bacteria. But for now, we'll send it back to the studio. Mike, take it away.
All right, thanks for that, Devin, and we will find out how this all turns out in just a little bit. We do have phone tutors available until 5:30. Don't forget, you can give us a ring. We'll help you do your problem on air, and hopefully it makes a little bit more sense to you, and we can help you out with that as well. In studio, we have Mackenzie, a 6th grade student from Hart Elementary. And if it was her doing, she would say, everybody go back to school, wear a mask, but that way you can all see each other and go ahead and keep on going, right?
Yep.
I'm
All
with
right.
you.
Well, you know what, Mackenzie, before we get back to you, I've got another great problem for you to work on. We're going to go to the phones right now. Brooklyn, how are you today?
Yeah. Good.
All right. And what grade are you in, Brooklyn?
3rd grade.
All right. As soon as you're ready, let us hear the math problem that you're working on.
Okay.
Everybody go back to school, wear a mask.
James got 3 hits in each of his baseball games. He has played 4 baseball games. How many hits has he had?
Okay, Brooklyn, right? All right, so he played 4 games. Let's look at this as a picture. He played 4 games, right?
Yeah.
1, 2, 3, 4. By the way, go Dodgers, yay.
Oh, easy now. We're not going to start any of that business now, are we?
And so if he had 3 hits each game, let's do like 3 dots, okay? There's one game, 3 dots. There's another game, 3 dots. There's another one, and then 3 hits his last game. So Brooklyn, how many total dots do we have in all? Let's count them together. What do you think? 1, count with me. 1,
1,
2, 3,
4,
5,
5,
6, 7, 8.
8, 9, 10, 11, 12.
That's it. So we have a total of how many?
12?
12. Because, Brooklyn, we
Oh,
have...
we have a total of 3.
Yeah,
no, 12.
are you learning multiplication yet, Brooklyn?
Yeah.
Okay, then can you turn this into a multiplication problem for me?
Yeah. 4
Uh-huh.
times 3
Equals...
equals
What's our answer?
12.
Equals 12. There you go. So we know that we have 4 groups of 3, and our solution is 12. There
Nicely
you
done,
go.
Brooklyn. You've got yourself a meal courtesy of our friends at Grillenberger for that one. Never too young to start calling in to do the math right there, learning your multiplication in 3rd grade. That's exactly why we're here, to help everybody out. All right, Miss Mackenzie, time to get you cracking again. Here we go. Let's take a look at the problem. This one satisfies actually for your grade, 6th grade, number sense. What is the smallest positive 5-digit integer with all different digits that is divisible by each of its non-zero digits? So that means you can have a 0 in the number. You don't have to, but you're allowed to.
All right.
So you're looking for the smallest number.
All right, Brooklyn, grab a pen. What are you thinking?
You're gonna-
What numbers do you automatically think of? Smallest 5-digit number.
Smallest 5-digit number?
Uh-huh.
That
Re-
I
Remember that if I have the number 12, that's 2 digits. So we want a number with 5 digits. So we're in the thousands, right?
Yeah.
Okay. So what are you thinking? What should we start the number with? Think smallest.
A 1?
Perfect. Let's start with a 1. Okay, what do you think should be next? Think, what are your 5 smallest numbers?
1, 2, 3, 4. 0 count. The 0 count?
Yeah, it does.
0, 1, 2, 3, 4.
Okay, how can you make a number using those numbers? So
So I would say is
We
write
know.
those numbers up there first
Yep.
so you've got
Okay.
them. There you go.
there we go. We have 0, 1, 2, 3, and 4.
Oh, did you write them? Oops.
So how can you make a number? You've started it with 1 because we can't really start it with 0, right? So you started with 1. What do you think should be the next number?
Maybe.
Do you want to go 4?
Yeah, I was gonna say 4. Yeah.
Well, if we go 4, okay, so if I'm thinking 14,000,
Right.
is that kind of higher than maybe
Yeah.
like 12,000?
Okay.
Do you see what I'm saying?
Yeah,
so
yeah.
where should we go next? What would be the smallest thousand?
0.
Okay, let's put a 0. So you have 10,000 something, right? So where do you want to go next?
A 2.
Okay. And,
A 3.
okay,
And then the 4.
okay. So they have to be divisible by all 5, all 4 of the numbers, right?
Well,
Not
right, because the
the
0
0,
obviously
you
isn't going to
can't.
work. Now,
Okay.
think about this, Mackenzie. Can you divide that number by 1?
Yeah.
Yeah, you know, right?
Yeah.
Easy enough, right?
Yeah.
And we can divide it by
going.
2, right?
How do you know you can divide it by 2?
2 divided by, or the 2,
How do you know you can divide that big number by 2?
because it ends in an even number.
Perfect. Well, what about 3? Do you know the divisibility rules for 3?
I don't think I do.
Well, if the digits all add up to a multiple
Okay,
of
I've heard that
3,
one.
so what do the digits add up to?
I write it down. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10.
Is that going to work?
No.
No, that's not going to work, is it? So we know we can't use 1, 0, 2, 3, 4. So what should we do? What should we get rid of and add on?
So you're at 10. Think about
Yeah, that-
doing divisibility by 3. You're at 10. What
Okay.
next number going up
Think
would
of
be divisible by 3?
think about, yeah,
12.
okay. In order to get to 12, then what number are we going to need in there? Which number should you take out? Okay, okay. Between 10 and 12, what's the difference?
2.
It's 2, right? So how, we need to go up, how many, one of the numbers needs to go up by
2.
2. So which number do you think you want to take out?
The 4.
Okay,
And make it a 6.
try it. Okay, so we know that the 1 goes in, we know the 2 goes in. Now let's add up all those numbers.
Okay. 1 plus 2 equals 3, plus 3 equals 6, plus 6 equals 12.
Okay, so we know the 3 goes in. Do you know the divisibility rules for 6 though?
No.
It's pretty simple. If 2 and 3 both go into the number, 6 will go into the number.
Oh.
Does 2 and 3 both go into the number?
Yes.
Will 6 go into the number?
Yes.
Have we
Okay.
solved it?
Yes.
There you go.
There you go.
10,236. Nicely done. For your effort today, Miss Mackenzie, you've got yourself a meal courtesy of our friends at Broken Yoke. So congratulations on that. All right, time to head out and about once again, indeed this time further out to outer space.
Have you ever wondered how something like this turns into something like that? Find out next on Real World.
Here at NASA, everything begins with an idea. But somebody has to take that idea and turn it into a vehicle that flies. A physical model is a great way to begin. Models allow engineers to test their ideas before a full-scale version is even built. Let's check in with Kevin McLean at NASA's Langley Research Center so he can show us how these models are made.
So to make a physical model, we start with an idea that's given to us by a researcher or an engineer. And we sit down, we talk about what we want to build and what those parameters of that test is going to be. So for a physical model, math is very important because there's a lot of different variables that can come up where you need to know the different weights of materials compared to what a finished product is going to be at your end weight of the model. Then you're going into measuring what dimensions. So every part of that model has to be measured and constructed to a specific scale So if you start with an actual airplane in real time, you need to know how to dynamically scale that down, or just scale it down to the ratios compare with the fractions of different parts and how things move within space. And then you need to know, like for when you're cutting materials to actually put into these laminates or these skins, you have to know what a hypotenuse is going to be, so you can actually put everything together and splice in really weird kind of contours that are going to be in your model, because nothing's ever going to be perfectly straight. So there's a lot of different geometry that goes into creating airfoils. Most of the physical models we build here in the model shop, if they're not tested here on center, we do send them elsewhere. And here on center, we can put it in NTF, and that's a cryogenic tunnel, so it can get really, really cold and kind of substitute what happens when a plane gets really, really high in the atmosphere. And then we have like some of the 3D printed models. They go into our low speed tunnels, which can be 12 foot, or our spin tunnel. The spin tunnel looks at what happens in a flat spin if a model's falling out and it stalls. How well can that model gain its kind of footing back and start flying again without crashing, or how bad does it crash? So model can help make a prediction by allowing us to visualize and understand what happens when we put something that we've never done before into a situation or an environment that we just can't understand.
Technicians use math to build more than just physical models. They're building prototypes to bring innovative new ideas to life.
Whether it's a physical model or a computer simulation, researchers use math to take an idea from concept to flight. I'm Michelle, and I'll see you next time on Real World.
All right, we've got another fabulous problem for Mackenzie to work on, so let's take a look at it together. Those of you at home can work on it while Mackenzie does here in studio. An abundant number. Have you ever heard of an abundant number before?
No.
No, see, a big day for you right now. An abundant day, let's say. All right, anyway. An abundant number is a positive integer such that the sum of its proper divisors is greater than the number itself. The number 12 is abundant because we take all of the factors, the divisors, right? 1, 2, 3, 4, and 6. We add them all up, and that is greater than 12, right? Because 6 and 4 is 10, and then 3 is 13, 15, and 1 is 16, right? It's bigger than the number itself, 12. What is the smallest abundant number that is not a multiple of 6?
Okay, so 12 is a multiple of 6, right?
Well, we're
So
not
we
using
need
that.
a number, right? Where do you think we should start, Mackenzie?
I'm not sure.
Well, can we start simple with, say, 6?
Okay.
Well, we can't start with 6. It's a multiple of 6, right?
Right.
Yeah.
Okay, let's start with 4.
Okay.
Well, hold on, sister. Let's go up from there. Let's
Okay,
start.
let's
so
go
let's
ahead.
start one up.
Okay, let's start one up. So start with 5. Let's start with 5. Well, that's a prime number, right? Let's go to 8. Start at 8. So what are the factors of 8?
Right.
Yeah, you can write it.
1 and 8, 2 and 4.
Okay. When we do this, are we including the 8?
You're not going to put the number
We're not
itself
going to
in
put
there.
the number itself in there. We're
Okay.
just doing the 1, the 2, and the 4, correct?
Right.
Okay, so we want the 1, okay, but we don't want to include the 8.
Okay.
So what is 1 plus 2 plus 4?
1 plus 2 is 3, plus 4 is 7.
Okay, is 7 greater than 8?
No.
No. So let's go ahead and do this. We know that this is going to be less than 8, correct? Okay, what's the next number after 8? What comes
9.
out? 9. Okay, let's try 9.
9 would be 1, 3. What did I do?
That looks it, right?
Yeah.
1 and 3. And what does 1 and 3 equal?
4.
Okay, so we know that that's also less than 9, right? So show our less than symbol, then 9. So we know that that doesn't work. What about 10?
10 is 1, 2, and 5.
Okay,
5 plus 2 is 7, plus 1 is 8. So it's less.
less than that's not going to work. So Then we don't want to do 11, we don't want to do 12, right? 13 is a prime number, we don't want to do 13. What about 14?
Okay, 14 would be.
Yeah, if you want to write up above, you can write up there
Okay,
too.
14. 1, 2, not a 3, not a 4.
There you go. Okay, what do those equal?
That would be 10.
Okay,
So less.
so let's go to 15.
15, okay. 15 is 1, 3,
What do you think?
it's less.
Yeah. And 16?
1, 2, not a 3, 4,
Okay,
8 plus 4 is 12, plus 2 is 14, 15, so less.
less. And we don't want to do 17. Why do we not want to do 18?
Multiple of 6.
Exactly. And 19 we can't do because it's a prime number. So our next one is?
20.
Okay. If you need to come on over here, you can.
Okay. And I said 20,
20.
10, not 3, 4, and 5.
Okay, add those numbers up for us.
4 plus 5 is 9, plus 10 is 19, 21, 22.
Is that greater than 20?
Yes.
Have we found our answer there?
Yes, we have.
Yes, we have. There you go. So the smallest abundant number is, what number is it?
20.
Very well done.
There you go. And there are a lot of students, and trust me, this has happened in the past, where they will go through that process and they will put 18. And 18 is an abundant number. But with the criteria here, the answer cannot be a multiple of 6. That's why you need to make sure you look at the whole thing, and then you go, oh yeah, 18 is one, but I can't use it for this. And then you go to 20, and then that way 20 works right there.
Probably maybe the best thing to do is make a list of those multiples of 6, so you know, okay, I don't need to
Then
go to
cross
that
them out.
number. Cross them out.
There you go. Nicely done. All right, you know what? We do have one more opportunity. We're going to head back out to Taft College and visit with Devin and see how all the germs are going.
Hey, thanks a lot, Mike. Back here at Taft College at the biology lab here with Greg Galling. He's a professor of life sciences. We've been doing a bacteria experiment, pressing fingers on petri dishes, letting them incubate for a day, and seeing what comes up before and after we wash our hands. The students here in this class took part in this yesterday. They're collecting their dishes from a day in the past. Let's see how this turned out for everybody.
All right.
Let's take a look here, starting off. Sir, your name, please.
Ahmed.
Ahmed. Thanks for joining us, Ahmed, and thank you for sharing your bacteria with us. So, let's take a look. Tell us some of your observations here.
So this side has a lot more bacteria than this side. I'm guessing that this side was the pre-side and this is the post-side because I learned earlier that actually when you scrub your hands a lot, it reveals some of the natural bacteria that we have on them. It's called normal flora. So when you scrub it a lot, then a lot of that bacteria will show. And not all bacteria is bad. So that bacteria is actually good for us. So we see here on the post side, after scrubbing, it exposed it and it let it grow a lot. So I'm guessing that this side here was pre and that's post.
That's a lot of confidence to say, hey, my hands are cleaner before I wash my hands.
Hopefully.
To be able to say that. That's fascinating. Is that what you thought was going to happen?
I think so. I've done this lab in a different class and I got sort of similar results. I'm hoping that this is the post side, but if it's the pre side, that's probably bad news.
That's right. Well, let's see if anybody's got some bad news here.
Well, I can't say too much about mine. I mean, this is my pre-side, and they look about the same, so.
Well, that's interesting.
I guess.
One thing when you're looking at them, again, each bacterial species has a different way that it grows, different colors and sizes. Look and see on your post, do those look like a lot of different types of colonies? Do you have more different colonies on the pre?
Well, seems like there could be a different colony that did come out after hand washing.
And you can observe that just by looking at the size of the colonies, the colors, the shapes.
So It seems like they have about the same mound, like Professor Goling was saying. They can spread out, they can grow in heights or in masses. It seems like there's just a few the same sizes, and they all have the same color, it appears.
And what's interesting is you use the same 3 fingers, but on the pre, different mounds are growing larger than on, let's say, the post. So like we could see different clusters on different fingers, and you use the same 3 fingers when you press down. So that's really interesting. Who else can we share with?
I saw some good ones earlier. It went from hardly anything on the pre to quite dirty on the post. Anybody willing to share? We could black out faces, I guess. It's okay.
Okay. So let's take a look.
Oh, that's a good one.
Oh, wow. Yeah, you're right. I wouldn't want to talk either. So what really stands out when we look at this?
Well, you know, when we do this with students, if they haven't done it before, they're always amazed that, and they think they messed up. They think, oh, I must have put my post hand on the pre side, you know, switched them around. And they just can't believe that their hands would have gotten dirtier from washing them, because that's what we're always taught. Hey, well, clean your hands, wash your hands. And, you know, the first thing they think, oh, it must be the water at Taft College, that's it. You know, this is the water, this is good water. This, you know, it would be criminal if we had that much bacteria in the water here, and we don't. It's good. And what a lot of students and people in general don't realize, what's happening is, on the pre-side, that's everything that you've touched during your day, your steering wheel, for instance, and you're just transferring those bacterial cells onto the plate. When you wash your hands, you're rubbing off some of the skin cells, and those are getting rinsed down the drain, and there's just this jungle of life underneath those skin cells. Again, we've got, you know, the average human body maybe has 1 trillion human cells, 1 to 10 trillion, and we've got about 10 times that amount of bacterial cells in us, on us. So what you see in the post, this is what we'd call normal flora. This is stuff that we all have. It's generally speaking not pathogenic, and in many cases it's beneficial to us. It can prevent other organisms, certain pathogens, from actually growing. They're all trying to compete against each other for space, for nutrients, and if they've adapted to live on our fingers, that gives them, you know, sort of a leg up, so to speak, with that.
The message isn't necessarily don't wash your hands.
Right.
The message is when you do, some of the healthier, more natural bacteria that's already in you is exposed, and you can kind of see what's there.
Yeah, and if that gets on you or somebody else or your sandwich that you're eating, it's, you know, it's already part of you, so it's not necessarily a bad thing. Yeah.
Well, Greg, thank you so much for having us here to share our appreciation for allowing us in here at Taft College. We wanted to grant you some of our traditional do the math, congratulatory tile, post that, place that wherever you'd like, put it on display where you can.
Thank you very much.
Hey, thank you very much, everyone. That'll do it here from Taft College. Until next time, we'll send it back to the studio. Mike, take it away.
All right, thanks for that, Devin. Also, thank you to everybody out of Taft College. That was certainly informative. And hopefully wherever they put that tile, it's nice and clean right now. We do have phone tutors available until 5:30 most Tuesdays and Wednesdays throughout the regular school year. We want to say thank you to Mackenzie, a 6th grade student from Hart, for coming in today. Did you learn anything today?
Yes.
Quite a bit, I think, right?
Yeah.
A lot of stuff. Now, the more important question is, did you have any fun today?
Yes, I did.
All right, good. I'm glad you had fun. I'm glad that it was worth your while for coming in. We certainly do thank you for that. Do remember, until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.